So for this question, which asks us to devise the systematic IUPAC names for a couple of different molecules, I'm not going to do all of the answers for you. I am going to do two of them, and then I'll let you do the others on your own. Let's take a look at the first one that I've chosen randomly. In order to be able to come up with a systematic IUPAC name, you first of all have to determine what the longest carbon chain is in the molecule. Now, one thing we might be tempted to do as English speakers, those of us who are native English speakers, I suppose, is to just look at the one right along the horizontal line and go left to right, because that's the way English is written. 1, 2, 3, 4, 5, 6, and call that the parent chain. Aha! Now, that'd be fine if that were the longest chain, but is it the longest chain? Well, keeping in mind that I don't necessarily have to go left to right, and I could go along any of the chains in any direction that I wanted, it probably isn't the longest chain. For example, I might instead try, so that's a 6-carbon long chain just going horizontally across the axis there. I might try going up here, 1, 2, 3, 4, and then going down here, 5, 6, 7, 8. Ooh, that's 8 carbons long. That's longer, so that would be a possible direction. Or, what if I try a different direction? Could I go instead along this, 1, 2, 3, 4, and then I go 5, 6, 7, 8, 9. That's even longer. That's interesting. Is there another direction that I could go? Well, what if instead I started here and I called that carbon 1. I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's probably going to do it. I think that might be the parent chain and is certainly the longest chain that I think we're going to be able to come up with for this structure. The next question then is, which direction is the correct direction? See, I could number from 1 to 10 going in that direction, but I don't necessarily have to do it left to right. It could be right to left. So what if I numbered in the opposite direction and called that carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10? All right, those are both, ways I could do it. Which one is right and which one is wrong? Well, the one that's right ends up being whichever one gives you the lowest number at the first point of difference. I realize that sentence might sound extremely confusing. Please allow me to elaborate. Foremost, let's see if we can come up with a name for this chain. 10 carbons, a 10-carbon long chain is called decane, so that will be the parent chain name. We just need to identify the substituents. So what I'm going to do is circle our 10-carbon long chain like this. Ooh. Ooh, there we go. That's our 10-carbon long chain right there. Then we're going to note where the substituents are coming. Substituents are just anything dangling off of that chain. So I've got a CH3 dangling off of carbon 5 or 6, depending on which direction I go. I've got a CH2, CH2, CH3 dangling off of the same carbon. I've got another CH3 dangling off of carbon 3 or 8, depending on which color scheme I pick. Let's see if we can figure that out. So, first of all, coming off of carbon 5, I've got 1 carbon long. A 1 carbon long chain in the world of IUPAC is called methane. However, this is not a methane all by itself. This is a methane that is a substituent. So I replace the suffix "ane" with "ill." So coming off of carbon 5 or 6, we'll do the blues first. We'll do the blue direction first. If I go in the blue direction, this is a 5-methyl. Now, also coming off of carbon 5, blue notation, I've got a 3-carbon long chain. 3-carbon long chain is called propane. However, this is not a regular propane. It's a propane dangling off of a parent chain, which means it's a substituent, so I replace the suffix "ane" with "ill." So coming off of carbon 5, I've got propyl. Coming off of carbon 8, I have another methyl group, so I would go ahead and write down 8-methyl. So if I were numbering in the blue direction, it would be 5-methyl, 8-methyl, 5-propyldecane. However, that may or may not be the right direction. Let's see what it looks like in the green direction. Coming in the green direction, I've got a methane or a methyl group attached to carbon 3. So I could go 3-methyl. And then, continuing in the green direction, I have coming off of carbon 6, I've got 6-methyl. And also coming off of carbon 6, I've got 6-propyl. So that would be the number scheme for the green direction. Which one is right, which one is wrong? Well, you'll see that 3 is smaller than the 5s, but 6 is smaller than the 8s. Which one do I pick? The one that ends up being right is, once again, the one that gives you a smaller number at the first point of difference. So let's go ahead and look down. Alphabetically, M comes first, so I'll look at the M's first. I've got a 5 here and a 3 here. 3 is smaller than 5, so I'm done. The green direction is right. It doesn't matter what happens after that. That makes sense? So once you break the tie, and if these had tied, then I'd go down to the next alphabetical thing, and I probably should have put this propyl at the same level as the other propyl, but and I would continue going until I break the tie. The first location which there's a difference, the lower number is the one that is the winner, and everything else after that point is irrelevant. So the green direction is going to end up being correct, so I'm going to go ahead and erase my blues. Based then off of this molecule, which is, once again, a decane, I've got, if I can write that correctly there, I've got a methyl coming off of carbon 3, another methyl coming off of carbon 6, and a propyl coming off of carbon 6. I alphabetize them. M comes before the letter P in the English alphabet. And I can consolidate the methyls by just saying 3, 6 dimethyl, and I'll put a hyphen, 6 propyl, oh gosh, I'm going to give myself some room here, decane. That will be the systematic IUPAC name for this structure. Now real quick, I want to give you a heads up, sort of an introduction to a piece of software that can allow you to cheat. Now students, I don't want you to cheat, but sometimes it's nice to have a piece of software that you can manipulate and check your answers with, especially so that you can see how changing the structure would change the overall name. There are 2 different software programs of which I'm aware, though there are probably others. One is called ChemSketch, and one is called ChemDraw. Both of them have the ability in them to allow you to draw any organic molecule you want, such as this, and have the program automatically spit out a systematic IUPAC name for you. And then you can change the molecule and do it again and see how changing the molecule structure changes what happens to the name. Hopefully if you use that, if it's useful for you, you can, well, it will help you get a better grasp of how IUPAC names for simple alkanes work. I am aware of the fact that ChemSketch does have a free version that you can download for free off of the internet. I don't know about ChemDraw, so I'll leave that up to you if you want to try either of those software programs. Let's take a look then at our next example. This question takes advantage of our simplified line bond structure, so each one of these points is a carbon atom. We've left out the hydrogen atoms. Not too bad. So once again, I'm going to try to identify what the longest carbon chain is. I might be tempted initially to just start at the sort of middle chain and number left to right. That would be 6 carbons long. But that may or may not be correct, because what I'm trying to do is find the longest chain. And if there's a chain longer going in some other direction than 6, then it ain't going to be 6. And I'm betting that's going to be the case. I'm going to go ahead and wipe those numbers off. What if I start numbering up here? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's longer. That's longer. And as I look at that closely, I don't think I could come up with any different chain that's going to be longer than that. I mean, if I start here, I go 1, 2, 3, 4, 5, 6, 7, 8. Oh, yeah, actually, I could do that way. I could go, I'll use the black marker here. So I could go here 1, 2, 3, 4, 5, 6, 7, 8. So those are 2 different potential chains that I could use. Which of those would be the better one? Well, the one that I'm going to want to pick is the one that has the fewest number of branch points on its substituent. So if I look at the green one going down, I've got a branch point right there. I've got 1 branch, and then I've got 2 branches here. So, sorry, now I've got another branch. So I'm just looking down this green one right here. I've got 1, 2, 3 branches. These 2 groups coming off of here, and that group dangling off. Whereas if I do my the black chain here, I've got a branch coming off of its carbon 5, and then I've got this other branch that's a branchy branch coming off of its carbon 4, and that might be a little bit more confusing. So you want substituents to be as unbranchy as possible. So I'm going to go ahead and pick the green as being my parent chain to be able to achieve that. Hopefully you're okay with that, because numbering or naming, if I were considering this entire appendage down here to be a substituent, it would be a pretty complicated, hairy substituent to do. The next question we have to address then is direction, because I could just as easily number from the bottom up 1, 2, 3, 4, 5, 6, 7, 8. So one of those is going to be right, one of them is going to be wrong. Which one is right, which one is wrong? The one that's right is the one that has the smaller number at the first point of difference. So let's go ahead and write those different things out. First of all, an 8 carbon long chain is called octane, so this is going to be the parent name of this chain. If I number in my green direction, I've got, coming off of carbon 4, I've got a single carbon dangling off of carbon 4. A single carbon as a substituent is called a methyl, so I've got a 4 coming off, or a methyl coming off of carbon 4. Coming off of carbon 6, I have another single carbon coming off of that, so I've got 6-methyl. Coming off of carbon 5, I've got a 1, 2, 3 carbon long appendage attached to that. 3 carbon long is called propane. So coming off of carbon 5, because propane is a substituent, I call it propyl. That would be the green direction. Now the black direction, if I'm numbering or looking at the black numbers, I've got a 1 carbon coming off of carbon 3, so that's 3-methyl. I've got 1 carbon coming off of carbon 5, that's 5-methyl. And I've got, coming off of carbon 4, I've got 4-propyl. So what I'm trying to do is look at these. Where is the first location which there is a difference between one guy and the other one? Or between one option and the other one? The very first difference is right here at 4 versus 3. That's the very first location which I have a difference. And so the black direction is going to be the one that I'll go. So I'll go ahead and cross off my green numbers here. And then I'll lay down my name. So the parent name is octane. Coming off of this, and I'll go ahead and draw or circle my parent chain here. My parent chain is this 8 carbon long thingy here. You'll notice that coming off of its carbon 3, there is a methyl. So I've got 3, and I have another methyl coming off of carbon 5. So write down 3,5 dimethyl. And then coming off of carbon 4, I've got a propyl. So I'll write down 4-propyl. And then octane. And, you know, I've kind of run out of room, but what you'd actually do if you wanted to get this totally right is write the octane up here, and you would not have a hyphen there. So it's 3,5 dimethyl 4-propyl octane, and that is the correct answer, or IUPAC name for this structure.